Welcome to Census and Industrial Instrumentation. The next topic is flow measurement. Flow measurements are important in a number of applications such as drinking purpose, agriculture purpose, industrial purpose. So this measurement of flow is very important in many applications. The most prominent are in drinking applications, we need flow measurement. In agriculture, we need this flow measurement. And in industrial purpose, we need this flow measurement. These are the broad areas where we use flow measurement. What is the necessity of this flow measurement? Why do you need this flow measurement? In construction purpose, we need flow measurement wherein we require what is the rate of flow, and to store water for proper utilization also we require to measure the flow, and to know the volume of liquid and rate of flow we require this flow measurement, and in many laboratories we use this flow measurement. So in construction, and to store water for proper utilization, to know the volume of liquid and rate of flow, and in laboratory we use this flow measurement. One is volumetric, the other one is weight, on weight basis. For solids we use weight per unit or mass per unit. For liquids we require volume rate or weight rate. For gases, it is always measured in volume rate. So, the fluids generally can be classified as two types. One is incompressible, other one is compressible. The incompressible fluids are those which are in liquid phase, and the compressible fluids are in gaseous phase. Right? So the two basic ways of measurements are volumetric and weight basis. And solids are always measured on weight rate or mass rate. Liquids are measured in volume rate or weight rate, and gases are always measured in volume rate. And basically, fluids are of two types: they're incompressible and compressible. Incompressible fluids are those which are in liquid phase, and compressible fluids are those which are in gaseous phase. Right? So, the flow units are, what are the units of flow? Generally, the units are described flow measured can be of several types depending on the specific process needs the information. Most commonly used are the following: volume flow rate, flow velocity, and mass or weight flow rate that I have discussed in the last slide. Now we are looking at units. Volume flow rates are expressed as volume delivered per unit time. So the typical units are gallons per minute, meter cube per hour, or feet cube per hour. 1 gallon is 231. And flow velocity is expressed as distance the liquid travels in carrier per unit time. The typical units are meters per minute, Heat per minute. This is related to the volume flow rate by V is equal to Q by A. V is equal to Q by A, where V is the velocity, flow velocity, Q is the volume of flow rate, A is the cross-sectional area of the flow carrier. Right? The mass or the weight flow rate is expressed as the mass or weight flow per unit time. Typically, the units are kg per hour, pounds per hour. This is related to the volume flow rate by F is equal to P into Q. What is F? F is the mass or weight of the flow rate. Rho is not P. Rho is the mass density or weight density, and Q is the volume flow rate. So F is equal to rho into Q. What is F? F is the mass or the weight of the flow rate. Rho is the mass density or weight density. Q is the volume flow rate. Next, coming to Reynolds number and flow patterns. Reynolds number is defined as the ratio of fluid's internal forces to its drag forces. So Reynolds number is given as it is the ratio of fluid's inertial forces to the drag forces. The flow rate, the pipe diameter, and the density of the fluid are inertial forces, while the viscosity of fluid is the drag force. What are the inertial forces now? Inertial forces are flow rate, pipe diameter, and density. These are the inertial forces. Now, what is the drag force? Drag force is the viscosity of the fluid. So, Reynolds number is denoted by R suffix E, which is V E rho by mu. V is the velocity, flow rate. D is the diameter, pipe diameter. Rho is the density. So, inertial forces are three. One is flow rate. What is flow rate? Velocity. Pipe diameter D. Density is rho. So it is R suffix E is equal to V into D into rho by what is the viscosity? It is mu. So this comes the formula. So once again, I'll repeat everything. What is Reynolds number? It is the ratio of inertial forces to the drag force. What are the three types of inertial forces that we have? Three. There are one is flow rate, other one is pipe diameter, third one is density. Flow rate is V, pipe diameter D, density is rho. So V into D into rho. What is drag force? It is the viscosity. What is viscosity is denoted by mu. Therefore, Re turns out to be velocity d into rho by mu. This is a formula. So where Re is the Reynolds number, V is the velocity, rho is the density, mu is the viscosity of the fluid, d is the pipe diameter. If diameter and density remain constant, what are the terms that remain constant? Diameter and density. So diameter and density are constants for most liquid applications. Alright. So At low velocities or high viscosities, Re value is very low and liquid flows in smooth layers with highest velocity at the center of the pipe and low velocities at the walls where viscous forces restrain it. Does this mean low velocities or high viscosities? At low velocities or high viscosity, what happens? Re value is low. High velocity and low velocity is low, v value is less. High viscosity, mu value is high, v value is less. What happens? As Re is proportional to v by mu, where d and rho are constant, if v reduces and mu increases, what happens to the Ra value? You can see as v is in the numerator and mu is in the denominator. As mu increases, Ra value decreases. That means Re value is low for high velocity and low velocity and high viscosity. And as a result of this, the liquid flows in smooth layers, where with highest velocity at the center of the pipes and low velocities at the walls. This type of flow is called as laminar flow. What is it called as? Laminar flow. What is a laminar flow? What is a laminar flow? A flow where the liquid flows in smooth layers with high velocity at center and low velocity at walls. This is called as a laminar flow. Why does this happen? You can see R is proportional to V by mu with D and rho as constant for most liquid applications. As V reduces velocity and mu increases, Re reduces. As a result of that, liquid will flow smoothly in with high velocities at the center and low velocities at the walls, and such type of flow is called as a laminar flow. Hope you got it. Now, the corresponding Re values are 2000 in CGS system used in the applications and are used for the various parameters. Now, if you look at this is a streamline where this is a flow direction that is given, and these are the velocity profiles. You can see these are the three different velocity profiles, and this is a pipeline. So, the different types of flow. The first one is A. Here you can see a laminar flow, symmetric to the axis, and B is a laminar flow, asymmetric. Here this is symmetric, and here this is asymmetric, and C is the turbulent flow. You know, however, most applications involve the turbulent flow. Most applications involve the turbulent flow with Re values between 200 above 200 with Re values Reynolds number above 200. The turbulent flow occurs at high velocities or low viscosities. Flow breaks up into turbulent eddies that flow through the pipe with same average velocity that you can see in the image. Now, what are the classification of flow meters based on weight or volume and rate of flow? Let's look at the classification of flow meters. Flow meters based on weight or quantity or volume and rate of flow. Now, a rate of flow meter. A flow meter can be defined as one the fluid passing through the primary element in a continuous stream. It is defined as the one where the fluid passing through the primary element in a continuous stream. Rate of flow means quantity of flow per unit time. Is the rate of flow? A rate of flow means what does rate of flow denote? It is the quantity of flow per unit time. Examples of these flow meters are orifice plate, turbine meter, electromagnetic flow meter. What are the different examples of this meters? Orifice meter, turbine meter, electromagnetic flow meter. What is a flow meter? It is defined as one where the fluid passing through the primary element in a continuous stream. What is rate of flow? It is a quantity of flow per unit. The different examples are orifice plate, turbine meter, electromagnetic flow meter. What are the different other classifications of flow meters? The head type flow meters based on differential pressure measurements. Orifice plate, venturi tube, flow nozzle, pitot tube, electromagnetic flow meters, rotameters or variable arm meters. What is the classification of flow meters? Was head type flow meters based on differential pressure measurements. Orifice plate, venturi tube, flow nozzle, pitot tube, and this comes under head type flow meters. Second one is electromagnetic flow meters. Third one is rotameters. Fourth one, mechanical flow meters, positive displacement, and turbine flow meters. Anemometer type, cup type anemometer, hot wire anemometer. Under mechanical flow meters, we have positive displacement and turbine flow meters. And anemometers are cup type anemometer, hot wire anemometer. And the sixth one comes out to be ultrasonic flow meter. Seventh one is vortex flow meter. Sixth one is ultrasonic flow meter. Seventh one is vortex flow meter. Now, head type flow meter. In this head type flow meter, a restriction of known dimensions are placed inside this pipe where there is a flow, where there is a flow, a restriction of known dimension is inserted into the pipe. And what happens due to this at this inserted place is first we'll see we'll place a manometer here, and this is a pressure differential. We'll have a liquid. Now, due to this, there occurs a head loss or pressure drop will occur at this inserted restriction. And at this restriction, due to this, there will be an increase in flow velocity because there is a pressure drop. And the measure of this pressure drop and the measure of this pressure drop at this inserted place is the indication of flow rate. Once again, this is a known pipe and there is a flow, and we are inserting some restriction of known diameter, known dimensions, one and the same, known dimensions, and because of this, at this point, there will be a head loss or pressure drop will occur. And the measure of this pressure is nothing but the flow rate. What happens due to this head loss or pressure drop? There will be an increase in the velocity, and the measure of this pressure drop at this restriction is called as it will denote the flow rate of the liquid. Now, what's the principle of this head type flow meter? In this, a restriction is placed in the fluid, as I told you. Restriction creates pressure difference, same thing. Pressure difference indicates the flow rate, and this is based on the Bernoulli's theorem. Again, what is the principle of this head type flow meter? In this, a restriction is placed in the fluid path, and the restriction creates pressure difference, and the pressure difference indicates the flow rate. The relationship is based on the Bernoulli's theorem. Clear? Now, head type flow meter. The head type flow meters have a common feature in them that they produce a pressure difference when fluid flow is maintained through them. There is certain linear relationship between the pressure difference and flow rate of the fluid. There is always a linear relationship between the pressure difference and flow rate of the fluid. The head type flow meters follow Bernoulli's theorem. So they have a common feature of pressure difference, and they have a linear relation between the pressure and the flow rate, and these flow meters follow Bernoulli's theorem. What is Bernoulli's theorem? It states that in a fluid stream, the sum of pressure head, velocity head, and elevation head at a point is equal to their sum at any other point. So the sum of pressure head, velocity head, elevation head at any point is equal to their sum at any other point removed in the direction of flow from the first point plus the losses due to friction between the 2 points. So, what does Bernoulli's theorem state? In a fluid stream, sum of pressure head, velocity head, elevation head at any point is equal to their sum at any other point in the direction of flow plus the losses due to friction between the 2 points. So this you can see fluid flow through a varying cross-sectional area. This is area A1. This is the area A2. This is the area A1. This is the area A2. These are points B, C, D, E, B, C, D, E, F, G, H, I. This is a pipeline, and this is the flow, and this is the height H1, and here this is the height H2, and the velocity here is V1, and this is the velocity V2. The difference between these two is taken as ds2, and the difference between these two is taken as the ds1. Now description. Consider a flow tube of varying cross-sectional area and having a difference in level as shown in the previous figure. An incompressible fluid density, we have discussed this, what is incompressible fluid? Rho is assumed to be steadily flowing through the pipe. What are we assuming? An incompressible fluid is of density rho is assumed to be flowing through the pipe. The flow tube axis inclined above the datum line. Datum line Above this datum line, flow tube axis. Applying the Bernoulli's theorem, the relationship for the fluid flow under equilibrium conditions can be expressed as we are considering a varying cross-sectional area having difference in levels. And next one is incompressible fluid is flowing through the pipe steadily. And flow tube is inclined above the datum line. And now we are applying the Bernoulli's theorem to this. So this is the expression according to the Bernoulli's theorem. P1 by rho plus V1 square by 2G plus H1 is equal to P2 by rho plus V2 square by 2G plus H2 is equal to A. What is P1? P1 is the pressure per unit area at BD. P2 is the pressure per unit area at FH. And V1 is the velocity at BD. P2 is the velocity at FH. So it is P1 by rho plus V1 square by 2G plus H1 is equal to P2 by rho V2 square by 2G plus H2 is equal to K according to Bernoulli's theorem, where rho is the fluid density, v is the acceleration due to gravity, h1 is the height of center of gravity of volume BCED above the datum line, h2 is the height of center of gravity of volume FGIH above the datum line. What is rho? Fluid density. V is the acceleration due to gravity. H1 is the height of center of gravity of the volume BCED above datum line. H2 is the height of center of gravity of volume FGIH above the datum line. If the level of pipe is parallel to the datum line, we have assumed a curved one. If it is parallel to the datum line, this is the datum line basically. P1 by rho plus V1 square by 2G is equal to P2 by rho plus V2 square by 2G. You don't have this H1 and H2 again because they are at the same level. Now, if you simplify this, you'll get V2 square minus V1 square is equal to 2G by E into P1 minus V2. V1 is equal to A2 by A1 into V2 is equal to A2 by A1 is considered as M into V2. You can write Qm is equal to A2 by A1. So V2 square, if you take common, 1 minus you'll get M. If you substitute V1 in this at this point, you'll get 1 minus M square is equal to 2G by rho P1 minus P2. That is V2 square is equal to 2G by 1 minus M square into 2G into P1 minus P2 by rho. So V2 is equal to 1 by under root of 1 minus M square. We are taking this square to the other side, it becomes under root. So it is under root of 2G into P1 minus P2 by rho. Now we can write A2 V2 is equal to A2 by under root of 1 minus M square into under root of 2G P1 minus P2 by rho, where Q A2 V2 is equal to QR. So QB is equal to E into A2 under root of 2G into P1 minus P2 by rho, where E is equal to 1 by under root of 1 minus M square, which is called as velocity approach factor. Called as velocity approach factor. So QV is equal to E A2 under root of 2GPD by rho. QV CE A2 under root of 2GPD by E, and Q is proportional to P and D since all the rest of the parameters are constant. Now this is the orifice plate. It is basically a thin metal plate with circular opening. This is a thin metal plate which has a tab handle, and this is an orifice plate. This is measuring orifice, and this is a drain orifice.